In this video, we're going to start talking about the second case where we can calculate the change in enthalpy or change in the internal energy, which is if there is a change in the temperature while the pressure and phase are constant. And as we said before, and as we saw before in the previous video and the previous chapter, that the temperature has a very strong impact on the enthalpy and the internal energy, much more than the pressure. And this is what we are going to see here. And that's why this part will be like a big part of this chapter, because we need to figure out how to predict and calculate this effect of the temperature on the enthalpy and the internal energy. So we will start with the internal energy. So what we know about the internal energy is, and again, this is the case where we have only variable temperature while the pressure is constant, and there is no phase change. And what we know that the specific internal energy will have a behavior like this. This is exactly what we knew before. But what we can get from this plot is that there is some sort of a relation that we can get for a very small change in temperature, and this is what we see here. This is the temperature is increasing from T1 to T1 plus delta T. So this is a differential change in temperature, or an incremental change in temperature, whatever name you want to give. But for the differential temperature change, we will have a differential internal energy change, and this delta U that corresponds to this delta T is what we can use to get the relation. So if delta T goes to 0, if this change in temperature is very small, then this is going to be small as well, but the ratio of delta U over delta T will reach a limiting value, and there is a slope that we can get from this, which is the delta Y over delta X, which is delta U over delta T. We know from thermodynamics that this slope, which is delta U over delta T, is called the heat capacity at constant volume, which is denoted by CV. So CV is the specific heat capacity at constant volume, and it's defined as we see here. It's the CV as a function of temperature. It's the change of enthalpy, or a specific enthalpy with respect to time at constant at constant volume. And there is something that we need to notice here, that this CV is a function of temperature, which means that the slope at this point is going to be different from the slope here, is different from the slope here. So there's something that we need to keep in mind, because this is going to be one big thing that we will be going through when we do the calculations later, inshallah. But for now, this is what we need to know, that CV, which is the specific heat capacity at constant volume, is equal to the slope of the plot of U and T. So it's the change of U with respect to T at constant volume. And the CV, and of course you can predict the units. It's going to be the units of specific enthalpy divided by the units of temperature. So it's going to be joule per mole or per kilogram divided by Kelvin. So it's kilojoule per kilogram Kelvin, kilojoule per kilogram mole Kelvin, or any alternative units in SI units or in any other system of units. So this is what we need to know about the CV. So if we you can rearrange the equation to be the change in internal energy equals CV dt. And this is function of temperature, and this is function of temperature. So we're getting the temperature dependent terms together and the rest of the terms together, which is du. And if we want to get the change of delta U from U2 minus U1 due to the change of temperature from T1 to T2, then it's going to be the integration. So I'll do the integration of du from which is the integration of this side of the equation from T1 to T2. And the equation, and this is the equation that we want to use, and this is how we can describe the effect of temperature on the internal energy. So if we know how CV can be mathematically represented as a function of temperature, we can do all what we want to do now, because we know the equation. This equation, again, this is important, that this equation is not valid for all the cases. It's valid for ideal gases, it's valid for liquids and solids, it's a good approximation. It's not exact, but it's a good approximation, and it's valid for real gases if the volume is constant. Again, there's something that we said about real gases, that real gases are not easy to describe mathematically, and there are equations, many equations that are made to describe the behavior of real gases. So again, this is something that we are not going to be going through in this course, but just to give you an idea that this works only for real gases if we are keeping the volume constant. So if I have a case where the temperature and volume are changing, and here we said that the volume must be constant. So if I have variable volume, so in this case we can break the change in internal energy into two steps. It's like we're creating a hypothetical path, as we said before. So we can say that this is a step where there is a change in volume at constant temperature, and there is a change in temperature at constant volume. So if we have a state of T1 V1, and then we have a change in the internal energy due to the change in volume. So you see here T1 is the same, and V1 equals V2. And then we have the second step where we have a change in temperature from T1 to T2, and V2 is constant. So we can say that delta U is delta U1 plus delta U2, and delta U1 is almost zero for if I have ideal gases. Okay, and we are saying this, I mean, I want to go back here because we say that this CV is the heat capacity at constant volume. Constant volume means that I'm keeping the volume constant. So if the volume is changing, then this equation is not going to be valid. So I need to make sure that I take all the parameters that are changing into account. So in this case, I have changing in volume, so I will deal with this as a case where the volume is changing only. And I am dealing with this as a case where the temperature is changing. This is what we just mentioned in the previous slide. And this is a case that we can see now. What we know that for ideal gases, for liquids and solids, the effect of volume is not there's no effect of volume on the internal energy. And we said before that in most of the cases the change in volume is due to the change in pressure. So if I change the pressure for liquids and solids, we said the pressure has no effect on liquids and solids because they are not compressible. And for ideal gases, we said that if it's still ideal and there is a change in pressure, there is no effect on internal energy. So again, this is what will be changing. The delta U is going to be 0 for this step, and then delta U is going to be the integral of T1 from T1 to T2 of CV dt. This is dt, but I think I forgot to put the letter T here. Anyway, so this is the equation that we have. So yeah, let's just take an example just to have a good idea of or just an idea how we can deal with this. So if we have nitrous oxide, 200 kilograms of nitrous oxide, that temperature increased from 20 to 150 at constant volume vessel. The constant volume heat capacity, so it seems it's a closed system. That's why we deal with the internal energy here. So the constant volume heat capacity of N2O is the given by the equation. So this is the equation. We're given here CV as kilojoules per kilogram Celsius, and this is the equation that we use. So we substitute here with Celsius in this equation. So what we have in this case, we have a closed system. We have, of course, the equation will be delta U plus the change in kinetic and potential energy equals Q plus work. There is no work here. It's a closed system. We are heating. The temperature is increasing, so there is no work. And we said before we can neglect the effect of internal energy, of potential and kinetic energy. And in this case, it's a closed system, so there is no motion and there is no change in the elevation. So the only terms that will have value are Q and delta U. So if I want to know the amount of heat, then I need to know what is delta U. So delta U is going to be the integral of CV dt. This is CV. Then I do the integration from T1 to T2. So the formula is very simple here. It's constant and constant multiplied by T. So all what I do for integration is add 1 to the power and divide by the new power. Here is T power 0, so it's going to be T power 1, and this is T power 2 over 2. So this is the integral. I substitute with the limits of integration from T1 to T2, and then this is the value of delta U, which is the value of Q. Of course, this is kilojoules per kilogram, and I want to get the total amount of heat, which is going to be mass divided by the specific internal energy change, which is going to give me the total amount of heat that is needed to raise the temperature. Yani for this case, this is an equation that we can deal with, and this is very similar to the shapes of the equations that we are going to deal with later for delta H and delta U. It's always polynomial, so it's constant plus constant multiplied by t plus constant multiplied by t power 2, and so on. So for the integration, I know the integration is something that many people are not happy with, but the integrations that we're going to do here are very straightforward integrations, so there is nothing tricky about the integrations here. I'm going to stop here, and next time we are going to talk about the effect of temperature on enthalpy. So continue next time, inshallah. Goodbye.